In this video, we're going to focus on the domain and range of a function. In the previous lesson about relations and functions, we've learned that the set of all possible input values is called the domain, while the set of all possible output values is called the range, right? And in the case of functions, since we denote functions as y equals f of x, where x is the input value and y is the output value, then we can also say that the domain is the set of all possible x values, and the range is the set of all possible y values. All right. Now, in general, we want our function to be a real valued function. Okay. In other words, the value of the function must be defined. Okay. So when we say the value of the function is defined, again, it must be a real number. And this implies that we must restrict the domain to only real numbers, so as to get real numbers for the range. Okay. However, just because we limit the x values to only real numbers doesn't mean that we will always get real y values. This will ultimately depend on how the function is defined. In other words, we have to look at what operations are involved in the function. But regardless, we just have to remember that we need to avoid function values that are not considered to be real. All right, so this leads us to some constraints or restrictions for our function values. Okay. Now, since we want our function to be defined or to have real values, then we don't want it to be undefined or imaginary. Okay, so let's focus first on undefined function values. We usually get undefined values if we have a rational function. So that's a polynomial over a polynomial. N of x here represents the it represents the polynomial in the numerator, while d of x represents the polynomial in the denominator. Okay, and again, for undefined function values, we have a rational function where the value of the numerator is any non-zero real number, so any constant value, and the denominator is 0. So for example, 4 divided by 0, 6 divided by 0, 100 divided by 0, right? And if this is the case, then we have an undefined function value, right? Now, you may be wondering why this is considered to be undefined. Okay, so we have a rational function, right? And a rational function, it involves division operation. And then remember that division operation and multiplication operation, they are inverse of each other. All right, so let's make a simple comparison. For example, let's say we have a fraction 6 divided by 2, which is equivalent to 3, right? Now, of course, this is a correct or true statement. 6 divided by 2 is indeed 3. And considering the fact that division is the inverse of multiplication, we can also check by multiplying 2. So we multiply 2 by 3 and we get 6, right? Now, how about 4 divided by 0? Is there a number, say, n, in the set of all real numbers that is equivalent to this particular expression? The answer is clearly no. It's because there is no number that when we multiply 0 by that number will result to 4, or in this case, any non-zero real number. It's because 0 times any number times any constant value or any real number is equal to 0. That's why this kind of expression is undefined. Okay. Aside from undefined function values, we also don't want our function to be imaginary. Okay, so an imaginary number, basically, this results when we have an even root of a negative number, like square root of -1, right? So this is something to do with radicals. Okay, so n here, this is the root or the index of our radical, and if n is even, like square root, fourth root, sixth root, and then coupled with a negative radicand, so radicand is the number or the value under the radical. So again, we have an even root or index, and then coupled with a negative radicand, then this is an imaginary number. Again, basic example of this is square root of -1. All right, so these are the two values that we need to avoid: undefined values and imaginary values. And as a consequence of these constraints on our function values, we need to restrict the x values or the domain. Okay. Hence, we have what we call the implied domain. Okay. So basically, for any function, the domain or the set of all x values is the set of all real numbers except those that will result to number 1 division by 0. So we have to avoid x values that will lead to division by 0, because again, this will result to undefined function values. Okay, and number 2, we also have to avoid x values that will lead to a negative radicand under even roots or indices. Okay, because again, this will result to imaginary numbers, right? So to find the domain, we assume first that it is the set of all real numbers, right? And then we exclude those x values that will lead to, again, division by 0 and an even root of a negative number. Okay, so let's try to work on some problems. For now, we'll focus on finding the domain. Okay, let's say we have y equals x squared plus 3x minus 4. Okay, to find the domain, we check if, number 1, if there is a possibility for the function to result to division by 0. And this will only be possible if we have a rational function. Now, in this case, this is not a rational function, meaning we don't have a polynomial over a polynomial for this particular example. It's just a simple polynomial function with a degree of 2, right? So it's a quadratic function, if you will. Then there will be no restriction in terms of being undefined, or in terms of being or in terms of having an undefined function value, right? So let's proceed to the second restriction. Let's check if it involves radicals, because if it involves radicals, we also check if the index or the root is an even number, because if that's the case, then we might be having a function that will lead to an even root of a negative number. Okay, so in this case, it obviously does not involve a radical. Therefore, there will be no restriction in terms of imaginary numbers. So for this particular function, since there are no restrictions, therefore the domain, we write the domain in this case as the set of all real numbers. Okay, since there are no restrictions for this particular example. This actually holds true for all polynomial functions. So if it's not a rational function, if it's not a radical function, if it's just a simple polynomial function of any degree, say quadratic function, cubic, so on and so forth. If it's just a plain polynomial function, then the domain is the set of all real numbers. Okay, and in this manner of writing the domain or presenting the domain, this is what we call the set notation. Okay, we can also present the domain using the interval notation. So for example, set of all real numbers, this means that it includes all real numbers or x values in this case, because we're talking about the domain. So it includes all x values from negative infinity to positive infinity. Okay, so again, these are the two ways we can present the domain or identify the domain of the function. So we have the set notation and the interval notation. Okay, we can also check by looking at its graph. So this particular function, this is a quadratic function, so its graph is a parabola, right? So this is its graph. This will go on and on without bound. This will also go on and on without bound. So this function can take on any x value, okay, because there are no restrictions. All right, next problem. So we have here y equals 2 over x minus 5. So this one, this is a rational function, right? We have a numerator, we have a denominator, and it does not involve any radicals, so we don't need to check for the second restriction. But there is a clear possibility for this function to be undefined, and that is if the denominator or the value of the denominator is 0. So we don't want that to happen. Therefore, we say that the denominator must not be equal to 0. In this case, the denominator is x minus 5. So we say x minus 5 must not be equal to 0. Okay, and then we solve for the x value that we need to avoid. Okay, so that would be x not equal to, so transpose negative 5, that would be positive 5. All right, so this is our only restriction for this function. Therefore, the domain is the set of all real numbers except x equals 5, or except 5, because it will make the function undefined. If we plug in 5, or if we replace x with 5, then we have 5 minus 5 in the denominator, that's 0. So 2 divided by 0, that's an undefined value. And again, we don't want that to happen to our function. So we write the domain as, so here I will be using the set builder notation. Okay, so domain is that x such that x is a real number and x must not be equal to 5. Okay, so this is how we write the domain or present the domain using the set builder notation. So set of all x values such that x is a real number, of course, and x must not be equal to 5. Or using interval notation, okay, so the domain is, so again, from the set builder notation, it says that the domain in this case is the set of all real numbers, and the only x value that we need to avoid is 5. So x equals 5. Okay, therefore from negative infinity, or meaning it includes all x values from negative infinity, and then we stop at 5. So this is excluding 5, that's why I'm using parentheses, close parentheses in this case. And then we take the union of this interval with the interval starting from 5, again not including 5, because we don't want our x to be 5, right? So from 5, excluding 5, to positive infinity. Okay, so these two are just the same. Okay, they mean the same thing. Set of all x values such that x is a real number and x must not be equal to 5, or all x values from negative infinity to positive 5 excluding positive 5, or 5 to positive infinity. So union between this interval and this interval. Okay, then from its graph we can also check. So this is the graph. So if we, for example, if we refer to the interval notation, it says here negative infinity to positive 5. This is positive 5, right? This is actually a vertical asymptote here, meaning our graph will not cross this x value, right? So we'll talk more about asymptotes later on. So again, from negative infinity to positive 5, this is the region described by this interval. So negative infinity, this is negative infinity to positive 5 here. And then from positive 5 to positive infinity. Okay. Next problem. We have here y equals square root of x minus 3. So we now have a radical and the index is an even number because it's square root, right? So there's a possibility for this function to be imaginary, right? And it will only be imaginary if the radicand is a negative number. Okay, so we want our radicand to be negative. That's why we say x minus 3 must not be a negative number. Therefore, we say it must be greater than or equal to 0. Okay, because all values greater than or equal to 0 are all positive values, including 0. Okay, so there's no problem if it's 0. We just want to avoid the radicand to be negative. Okay, so we solve for x now is greater than equal to positive 3. All right, so in this case, the allowable x values are x values greater than or equal to positive 3, right? For the domain, in this case, is the set of all x values such that x is a real number and x must be greater than equal to 3, right? Or using interval notation, that would be from positive 3, and since we have an equal sign here, so it includes 3, so we'll be using a bracket, right? An open bracket for this one because it includes it includes 3. And then from 3, since the allowable x values are the x values greater than equal to 3, so from 3 to positive infinity. Okay, so we always use parentheses for infinity because infinity is not a real number, right? Infinity is just a representation for extremely large numbers, so we cannot pinpoint the exact value of this number or of this idea infinity. That's why we cannot use bracket, for example, because we cannot include what we cannot pinpoint, right? So in this case, we use parentheses, always parentheses for infinity. Okay, so if you want to check why is it only x values greater than equal to negative 3, we can try to substitute, for example, 3. Let's draw a number line, for example. So let's say this is the point of interest in this case is 3. So let's say 3, okay. And then let's choose some test values. For example, x value less than 3, let's say 2. So this is test value for this interval. And then, for example, test value for x values greater than 3, let's say 4. Okay, so we can plug in, for example, 4. If we plug in 4, then 4 minus 3, that's 1. I mean, positive 1 to be specific. So there's no problem because the radicand is positive. If x is 3, then there's also no problem. This will just be 0. Now, if x is 2, where 2 is less than 3, if x is 2, then we get what? 2 minus 3, that's a negative number. And we don't want that to happen because it will lead to an imaginary number. That's why the allowable x values in this case is from 3 to positive infinity only. Okay, so this is going to positive infinity. Okay, we can also check using the graph. So like this one. So from 3, this is 3, positive 3. We only have a curve for this particular function at x equals 3 and then going to the right, going to positive infinity. We don't have a curve to the left of 3 again because this will give us imaginary function values and they are not included in our domain. Okay. Next example. So we have another square root function, in this case y equals square root of x squared minus 4. Okay, again we have an even root, so we don't want the radicand to be a negative number, so we say x squared minus 4 should be greater than or equal to 0, right? Then we solve for x. Let's transpose negative 4 first. So this will give us x squared greater than or equal to positive 4. Okay, and then from this inequality we can have two solutions, right? So if we take the square root of both sides of the equation, this will give us two solutions. One is x equals negative 2 and x equals positive 2. Okay, so for this particular example, for this particular function, we actually have to check by using a number line. Okay, so let's draw a number line. Let's say this is going to positive infinity, this is going to negative infinity. So we have 2 points of interest, x equals 2 and x equals negative 2. Let's say this is x equals 2 and this is x equals negative 2, right? So because of these values, x equals negative 2 and x equals 2, the number line is divided into 3 regions. Okay, so from the 3 regions, we can generate 3 intervals. Okay, so for this particular region, we have an interval from negative infinity to negative 2. And then from this region, we have negative 2 to positive 2. And then positive 2 to positive infinity. Okay, and then from each interval, let's choose some test values. Okay, and then later on, we'll plug in these test values so we can check if the value of x squared minus 4, the radicand, is either positive or negative. If it's negative, then we avoid those x values. If it's positive, then we include those x values in our domain. Okay, so for example, for this region here on the left hand side, negative infinity to negative 2, we can choose, for example, test value negative 3. Okay, and then from negative 2 to positive 2, let's say 0, right? And then from positive 2 to positive infinity, let's say we choose positive 3. Okay, and then we plug in each of these test values to our radicand and check whether or not, or check whether the value is positive or negative. So for example, if we plug in -3, or if we replace x with -3, then that would be what? -3 squared, so 9. 9 minus 4, it's 5. Basically, we just want to determine if the sign is positive or negative. So in this case, we have, again, -3 squared, that's 9 minus 4, so the value is positive. So if it's positive, then it's included in our domain. So there's no problem if the value is positive. So this is included in our domain. Let's check for this, the middle region for this interval. So our test value here is 0. So let's plug in 0. So if x is 0, then 0 squared, that's 0, minus 4. So we have a negative value. Okay, and again, we don't want the radicand to be negative. Therefore, this region here, represented by 0, is not included in our domain. Okay, and then lastly, for this region here, for this interval, we have 3. Okay, so let's plug in 3. 3 squared, that's 9, minus 4. So we get a positive value. Therefore, this is also included in our domain. Okay, so to write the domain in this case, we can just use the interval notation. It would be more convenient if you use the interval notation. Okay, so so this one, this is included, right? So from -infinity, so we say from -infinity to -2. In this case, -2 is included, right? Because if we plug in -2, then that's -2 squared. So that's 4. 4 minus 4 is just 0. It's not negative, so it's fine, right? So included, we include -2 for this one. So we write a bracket. Okay, and then we take the union of this interval with the next interval we have here. So this one going to positive infinity, from +2 going to positive infinity. And again, in this case, +2 is included, right? Because if we plug in +2, then there will be no problem for this one. So 2 squared, that's 4. 4 minus 4 is just 0. So it's not negative, so there's no problem if we include +2. So bracket +2 to positive infinity. Okay, so this will now be the domain for this particular function. Okay, so we can check the graph. This is the graph for this function. All right, so again, this is our domain. Okay, and if we check the graph, we can see that from -2 to +2, there is no curve at these x values, right? Because again, it's not included in the domain. Okay, next problem, we have here y equals x divided by x squared plus 1. So we have a rational function. If we have a rational function, then there may be some x values that will lead to division by 0. Okay, and we don't want that to happen again, so we say that in this case the denominator is x squared plus 1, and we say x squared plus 1 must not be equal to 0. Okay, so we solve for x, transpose +1 to the right hand side of the inequality. So x squared must not be equal to -1. Okay, and then if we take the square root of both sides of the equation, we actually get an imaginary number. In this case, it says that x must not be an imaginary number, and this works in our favor because we also want x to be a real number. Therefore, in this case, there is no restriction, so we say that the domain is the set of all real numbers. Okay, and this will be verified by its graph. Okay, so as you can see, it's a continuous function, or the graph is a continuous graph. So there are no interruptions, or there are no breaks in the graph. Therefore, the domain includes all real numbers. Okay, so this goes on to positive or negative infinity, I mean, and this goes on and on to positive infinity. Okay, so no restrictions for this one. The domain is the set of all real numbers. Okay, next we have y equals square root of x plus 2 all over x squared minus 9. Okay, so we have a combination of rational function and radical function. So let's focus on the numerator. Okay, in this case, the numerator is a radical function. So it's square root of x plus 2. Okay, and it's an even root. The index is 2. So we don't want the radicand to be negative. So in this case, we say x plus 2 must be greater than or equal to 0. Okay, and then we solve for x. So we have here x must be greater than or equal to negative 2. Okay, then we set this aside for now. Let's solve for, or let's move to the denominator. Okay, so let's check the denominator. The denominator in this case is x squared minus 9. Okay, and we don't want the denominator to be 0, so we say x squared minus 9. It must not be equal to 0. Okay, then we solve for x. So we have here x squared not equal to positive 9, and then we take the square root of both sides of the equation. This will give us x, and it must not be, or x must not be equal to positive or negative 3. Okay, so we have two solutions for this one. X must not be equal to negative 3, and x must not be equal to positive 3. Okay, so in this case, we have 3 points of interests. Okay, so we have here x equals negative 2, negative 3, and positive 3. So let's draw a number line, and let's check. Right, so we have here negative 3. Let's say this is negative 3, this is negative 2, and this is, for example, this is positive 3. Okay, so based on, or because of this x values, we have 1, 2, 3, 4 regions or 4 intervals. Okay, so as you can see here, from the first condition, x must be greater than or equal to negative 2. So it includes negative 2. So we say including negative 2, and we go to the right because it says here x value is greater than or equal to negative 2. Therefore, we actually don't have to worry with this x value, x equals negative 3. Okay, because this is already excluded in our domain. Okay, so from x equals negative 2, we go to the right. Okay, and then as we go to the right, so these x values here in between, these are included as stated by this condition or this inequality, x greater than equal to negative 2. However, we need to stop at positive 3, because at positive 3, according to this condition, x must not be equal to positive 3. So at this point, we draw a parenthesis, right? This means that positive 3 is not included in the domain. However, again, this inequality here says that x, or I mean the domain, is the set of all x values greater than equal to -2. So it will still go to the right, going to the positive infinity. It's just it doesn't include positive 3 in this case, right? So from positive 3 again, we go to the right, going to positive infinity. Okay, so we write the domain in this case as what? From -2, including -2, to positive 3, excluding positive 3. So that's a parenthesis, right? Then we take the union of this interval with the interval positive 3 to positive infinity. Okay, so this is now the domain of this function. And if we check the graph, this is the graph. So as you can see here, the curve starts at -2, this one. So no curve to the left of -2, again, because it, according to our solution here, x values less than -2 is not included in our domain. So it only includes x values greater than or equal to -2. So we start at -2 here. Then we go to the right. And then we do not cross x equals positive 3. At this point, we have a vertical asymptote. So the curve will not cross this x value. This is x equals positive 3. Okay. And then from x equals positive 3 again, excluding x equals positive 3, we go to the right up to positive infinity. Okay. Then lastly, we have, so number 7, we have here y equals 1 over square root of x plus 1. So we have another combination of rational and radical functions. Okay, so let's first focus on the radicand. Okay, radicand in this case is x plus 1. We have a square root, it's an even root, so we don't want the radicand to be negative, right? So we say x plus 1 must be greater than equal to 0, right? So solving for x, we'll get x greater than equal to -1. Okay, so set this aside for now. Let's move on to the other condition. Okay, the other condition is that we don't want the denominator to be 0 because it will result to an undefined expression, right? So the whole denominator in this case is square root of x plus 1. And we don't want this to be 0. Okay, so solving for x, we take the square of both sides of the equation. This will give us x plus 1 not equal to 0, or x must not be equal to -1. Okay, and then we compare both x values, or set of x values. Okay, so we have here x, according to this condition, the domain is the set of all x values such that x is greater than or equal to -1. However, according to this condition, x must not be equal to -1. Therefore, we exclude -1 and we only include x values that are greater than -1. So this is now the domain. We write domain, and then we say set of all x values such that x is a real number and x must be greater than -1, right? Or using interval notation, right? So the domain is from -1, excluding -1, right? So from -1 to positive infinity. Okay, so this is not the domain for this particular function. Let's look at the graph. So this is the graph. As you can see here, we have a vertical asymptote. Again, if you have vertical asymptote, the curve will not cross that particular x value. Okay, because at that point, or at that x value, the curve is undefined. Okay, so from -1, this is now the domain. These are the x values that are included for this particular, or these are the allowable or valid x values for this particular function. So from -1, excluding -1, because again, there's an asymptote. So from -1 going to the right up to positive infinity. So that's the domain, or these are the x values that are included or for this function. Okay, so going to positive infinity. Okay, so that's how we find the domain for functions.